Okay, so welcome to another video about calculus volumes here. So what we did first is we did what were called cross-sectional solids, and I called those magic yeast problems, where I had a solid that grew up and out of the page. So now what we're going to do is, instead of using magic yeast, we're going to spin something around and around and around and make a solid from the path that what I'm spinning traces out. So from the cross-sectional solid thing, we realized that if I want to find the volume of something that geometry doesn't give me a formula for, I can use the volume formula, where the volume is basically the area of the face created times dx, and what that does is it adds up a whole bunch of little slices for me to give me the total volume. Well, when I spin something, say like this thing down here on example 1, when I spin this around the x-axis, it looks like this vase over here. And if I want the volume of the vase, I don't have a geometry formula for that. So if I stick this vase in like a hard-boiled egg slicer and I slice it up into tiny discs and I add the discs together, each disc is going to look something like this. And yes, I think you should draw this on your paper. Each disc is going to look something like that, where this distance right here is my radius, and my depth is just dx because that disc was cut perpendicular to the x-axis. Okay? And again, the x-axis is kind of running through the center. Now my radius on the picture goes from the x-axis up to the y value on the curve, which means my radius is really just my function. And the volume of this disk is going to be pi r squared h, which in this case is going to be pi f of x squared dx. But since I need to add all the discs together, discs is hard to say. Since I want to add all of the discs together, I need to take the sum of all the pi r squared h's, right, and add all of those guys up. Now, the last time we did an r was when we had those semicircles and I had to divide something by 2. This time I don't need to do that because the function's height is the radius, because technically I've duplicated the function once above the x-axis and once below the x-axis, so the function itself is the radius, okay? So basically, I have to set that up, and I need my limits of integration. So like on this question, it says the region shown is f of x equals 2x cosine x on the interval from -2 to 2. So 2 plus x cosine x is f of x. And then I just have to evaluate that. So I'm going to pull up the calculator, and I am going to math 9, the integral from -2 to 2 of pi times 2 plus x cosine x end parenthesis squared dx, and get a volume of 52.428. Okay? Now, one of the things is a quick reminder here. When I'm putting integrals into the calculator, those parentheses get really annoying really fast. So if you put your integrand into y equals, as I did, and I again do math 9, I can just do the integral from -2 to 2. Oops, I forgot to type the 2 the first time. I can then do pi times y1 squared. And I don't have to worry about parentheses, and I should get the same answer. And I do. Yay! So just a reminder of those parenthesis things. Now, before I turn the page, I skipped the whole box here. Basically, what we just did is we found what's called the volume of a disk. And the reason this is a disk is because it's flat and it doesn't have a hole in it. The integral of that disk conforms to that generic formula, the integral from a to b of a of x dx. But what we also did is we found out that if I have a disk, every disk has a volume of pi r squared h. And r just happens to be our function. Okay? So, moving on. All right, find the area in the first quadrant bounded above by the square root of x and the 2 minus x. Okay, so let's draw this here. The square root of x (2 minus x) and below by the x-axis. So if I'm bound by these three things, I must be dealing with this region here. Let me highlight it. That's going to be better. Okay, so there's my region. It says find the area and then find the volume. Okay, so I got to find the area first. So if I want to find the area, I really need to know, let's see, where these things cross, because I'm going to section this into two parts. And let's see, so the square root of x equals 2 minus x. Yeah, I'm going to be lazy here, so let's get the calculator out. So if I do the square root of x and I do 2 minus x, I'll zoom 6 that. Here we go. Second calc intersect. Enter, enter, enter. My intersection's at 1, 1. Oh, that's helpful. I should have known that. So there's 1. And then this will cross the x-axis at 2. Obviously, this is not drawn to scale. And that's 1. So my area is going to be the integral from 0 to 1 of the square root of x dx plus the integral from 1 to 2 of 2 minus x dx. And so let's see. If I want to put this into the calculator here, I am going to come back here, math 9, and that's going to be the integral from 0 to 1 of the square root of x. Yes, we could have done this by hand, but this will be faster. And then I'm supposed to add this other integral, but I'm not going to be ridiculous. This other integral is just a 1 by 1 triangle whose area would be 0.5. I'm not that crazy. And let's see, what do we get here? 1.166687. One thing I can tell you is this should be an actual fraction. I think this should be 1 1/6. But your calculator's not that bright, so it's not going to realize that. So our area is exactly 1 1/6, which is 1.16 repeating. But if you didn't realize that, which is totally okay, you could write 1.166 and you'd be totally fine as well. Okay, so that's the area. And then it said, find the volume of the solid created when this region is revolved around the x-axis. Okay, so if I'm going to spin this around the x-axis, this guy's going to come down here like that. And we're going to get what looks like a snow cone. Actually, it looks a lot like a snow cone. So that looks a lot like a snow cone, right? So if I want the volume of the snow cone here, really, I'm going to have two parts to that volume as well. I'm going to have like this blue part up here, right? That's kind of the snow part of the snow cone. And then I'm going to have that other bottom part, this guy down here, which is really like the what do you call it, that paper holder that your snow cone comes in. So I need to find two separate volumes. So I'm going to do two separate integrals. So my first integral, come on, green, there we go. So my first integral is going to be the integral from 0 to 1 of pi r squared dx. And my radius in the first part goes from the x-axis up to the curve that's the square root of x. So I'm going to say, okay, so the square root of x is my radius, and there's the first part of my volume. And then the second part of my volume goes from 1 to 2, but now my radius over here goes from the x-axis to the line 2 minus x. Right? Right. And so we would just add those two things together. So let's see, over here and over there, I am going to math it out in the calculator. So math 9, 0 to 1 of pi times the square root of x squared, let's just call that x, shall we, dx, and then plus math 9, 1 to 2 of pi times 2 minus x squared dx. And I could have used y1 and y2 because those were in my calculator already. I just didn't feel like it. And if I hit enter, I get 2.61799. And yeah, why did I just do that? I don't know why I did that. I meant to touch this. Okay, and that's volume. I mean, this volume stuff, when you spin it, is not that hard. It's just pi r squared, pi r squared, pi r squared. So let's do another one. How am I doing on time here? I don't even know. 10 minutes. Okay, I got time. So find the volume of the solid created when the first quadrant region enclosed by the y-axis. Okay, y-axis, y equals 5, and y equals x squared, is revolved about the y-axis. Okay, so now this is a little bit different. I want to spin this very greeny green region around the y-axis. Okay, so if I spin this around the y-axis, I'm going to get kind of like a bowl-looking thing. But the thing is, whatever I spin it around, that's what I want to slice it with respect to. Because if I came through here and I sliced it vertically, that would just look weird, and nobody wants that. I don't want things looking weird. I want things looking nice. I want discs. So now my discs all look like this with their center at the y-axis. This outside radius here is the distance from the y-axis to the curve. So I need this function in terms of y. And my depth is just the vertical width, which would be dy. So this radius needs to be in terms of y. All right, so I can do this. Let's see. So I want to do the integral from 0 to 5 with respect to y. And I still am going to use pi r squared. But my radius now goes from the y-axis out to y equals x squared, which is also known as x equals the square root of y. So it's pi r squared dy. And this one's pretty easy to do by hand. So this is going to be pi times y, which is pi over 2y squared, which is going to be 25 pi over 2 is my volume. Okay? And I can do much the same thing with this last one. The region enclosed by this and the y-axis are revolved around the y-axis, but the thing is, I really like to see it. So you know what I'm going to do? Is I'm just going to change all the y's and all the x's. So I'm going to graph this as y equals x squared plus x minus 2. I'm going to bound it also by the x-axis, and I'm going to spin it around the x-axis. And now, no more y's are needed. Bye-bye, y. So what was that? I don't even know. I blocked it. Y squared plus y minus 2. Okay. So let's see. Y squared plus y minus 2. If I graph it, let's see. It kind of dips down there. If I use the powers of my noggin, I can realize that this is going to intersect at 1 and negative 2. So I'm going to take that region and I'm going to spin it. It's going to look like a top of some kind with kind of pointy ends. So if I spin it, it kind of comes up here and is rounded, right? Kind of like that. So my volume is going to be the integral from negative 2 to 1 of pi r. Well, my radius goes from the x-axis to the curve. So my radius is x squared plus x minus 2. There's pi r squared dx. Right? And then I'm just going to type that into the calculator. So let me come back here. I'm going to math 9, negative 2 to 1. Nope, nope, nope. I hit the wrong button. Negative 2 to 1 of pi times y squared. Nope, that's not the squared button. And I hit it so many times. How did that even happen? Wow. You're all thinking, okay, Mrs. Vibber, I've already done this on my own calculator by the time you finish. Okay. Why does this take so long to delete? Delete! Ah, okay. Oh god, they're still in my... Oh, gosh. Minuses, go away. Ah! Okay. Alpha, y1. Good, there's only one of those. And then I want to put a 2 up there. Ah! Fantastic. Da 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 da. 25.4469. Ta-da! Done. And that's it. That's volumes and solids of revolution that don't have holes in them. So one of the things that I need you guys to be able to do. So as long as you guys are feeling like you get what's going on, that's it. That's the end. So really bad joke. How does the solar system schedule parties? How does the solar system schedule parties? They plan it. Talk to you later.